forget the quizzes tomorrow and Friday.
And Friday.
And Friday?
Wait, let me look.
Yeah. How do you? Oh my god.
What can I eat?
Oh wait, this is easy.
I hope you guys brought your iPads today. Because we're gonna graph three-dimensional stuff. Oh, I thought this was straightforward. Ooh!
Wait, why is number 1 on the board?
Yeah, that's what I want to know. Why is number 1 on the board? Now, if you don't like the I hat, J hat notation, then change it to this, right? They mean exactly the same thing. It just means the x component is 2 and the y component is 3. You got to get used to that. So how do you compute the dot product? You multiply the x components, you multiply the y components, and you add them up and you get -7. My dog could have done that. That's number 1, for Pete's sake. Number 4. Are you doing? Is it April? I'll do one of them then. Which one you want to do, A or B?
B.
Okay. How do you find the angle between two vectors? That was the example yesterday. Oh boy. How do you find the angle between two vectors? The cosine of the angle is equal to the dot product. Now what is the dot product? You multiply the x components. Hey, that almost looks like the same as that. It's going to be A, and then you multiply the y components, -15, and you add them up. And then you divide that by the length of this vector, which is the square root of that squared plus that squared, which is 13. And then the length of this vector, which is the square root of 16 plus 25, which is 41. You guys can simplify that, right? Wasn't this the example we did on the board yesterday? Anytime you find an angle, you use this dot product thing right there. And then of course, cosine inverse it. And what does it come out? What does it say there? 107.650 degrees. On the test though, you're not going to have a calculator, so you just leave it. Yep. Okay, number 5. Wait a minute! How can you do 5 but not 4? That's what I want to know. Because 5, you have to actually do more work to get the vectors in component form. These, the vectors are in component form already. Oh, but 5 is up on the board. Oh gosh, this is a jolly holiday today. Oh, God. Do we need to draw a picture? I guess we should, yeah. A is, even though this is exact. Didn't we do a triangle yesterday? And if I look in the notes, is there a triangle one in the notes too? Yes. Okay, period 6. You guys telling, oh, we're so smart. Find the measurement of angle B. Anyway, this problem is on tomorrow's quiz. How do you compute the measurement of angle B? You form two vectors like this. What two vectors form angle B? Give me the two vectors. Okay, do BA first. Head minus tail, -3, and head minus tail, -1. You have to do head minus tail now, otherwise the vector is not pointing in the right direction. Okay, what about vector BC? Head minus tail, -2, head minus tail 2. Now, this problem is not the same as this problem now. How do you find the angle between two vectors? The cosine of the angle is equal to the dot product, multiply the x components, multiply the y components, add them together, over the length of this vector, which is the square root of 9 plus 1, and then the length of this vector, which is the square root of 4 plus 4. I will let you do the simplifying. Hey, this one might come out nice. Let's try it. 4 over, what is root 80? 4 root 5. No, doesn't come out that. I mean, kind of nice. So that angle is cosine inverse 1 over root 5. That's what you will write tomorrow. There's no calculator tomorrow. No, but there is a calculator tomorrow, but not for this problem. So you just leave your answer cosine inverse 1 over root 5. The one you're going to use your calculator for tomorrow is the airplane problem. If I change it to a rocket ship, is all hell going to break loose? I don't know. And then, come on! Wait, everybody. Oh, just when I thought you guys were good. Number 6. Given the points. Okay, here's part A. X, Y. A is 4, 0. B is negative 4, 0. Describe the set of points in the Cartesian plane such that vector AP, where's vector AP? Plus vector BP. If you add these two vectors together and then you find the length of it, you will always get 10. Now, can you see what that's going to be? No, most people, they can't see what it's going to be. So just do what it says to do. You're going to have to do this tomorrow too, you know. Okay, can we componentize vector AP? Here's vector AP. Can you componentize it? Yes, head minus tail. What is head minus tail? X minus 4, and then head minus tail, y. Okay, now what about vector BP? Componentize it. Head minus tail, head minus tail. Okay, now what does it say to do next? Add them together. How do you add two vectors in component form? You add the x components. 2x. Add the y components. And you guys in physics should be ashamed if you can get this. And then you find the length of it. How do you find the length of a two-dimensional vector? The square root of this squared plus this squared. So 4x squared plus 4y squared. And you set that equal to 10. What is this an equation of? Okay, some of you don't recognize it. Square both sides. 4x squared plus 4y squared equal 100. Divide by 4. X squared plus y squared equal 25. Now we recognize that as a circle. So if you don't know what to do, just do what it says to do. Componentize each one, add them together, and then find the length, set it equal to 10. Because there's going to be lots of problems when we get to the harder ones. You don't know what the heck to do, so just do what it says to do. Now part B says, what's the difference between A and B? Okay, don't answer me, theory 3. It says find the length of each one first, and then add them together equal, and set that equal to 10. Okay, what is the length of vector AP? Here's vector AP right here in component form. How do you find the length of that? The square root of this squared plus that squared, plus the length of vector B. Here's BP. How do you find the length of it? The square root of x plus 4 squared plus y squared, and then you set that equal to 10. Now simplify it. Now can you see that to simplify this, it's going to take a lot of algebra? You would have to move one of the radicals on that side, then you got to square both sides, but you can still have a radical, and then so you isolate it, you square both sides again, and then you got to complete the square. That takes a while. Does anybody like recognize anything? If the length of this vector plus the length of this vector is always equal to 10, hey, that's something we just learned, yeah? That's the definition of an ellipse, right? Remember, you have the two fixed points. Remember the string? You guys don't remember the string? Yeah. If the sum of the two distances from two fixed points is constant, that's the definition of the ellipse. And what are the two fixed points? The foci. So the center will occur halfway in between at the origin. And what kind of ellipse is this? Left, right, or up and down?
Left, right.
It's a left-right ellipse, so it's going to be x squared over a squared plus y squared over b squared is equal to 1. All you have to do is figure out a squared and b squared and you're done. But what is this constant? You guys remember? 2a. This is only 2 chapters ago. So we know a is 5. This is 25. And isn't c the distance from the center to the focus? So what is c? 4. And once you know a and c, how do you figure out b? C squared equals a squared minus b squared. Does that sound familiar? So 16 is equal to 25 minus b squared. Therefore, b squared is 9, and then you're done. Now, if you cannot remember that, then you just got to take this and then do the algebra. So tomorrow's quiz, what if I put a minus there? That's a hyperbola there. Or you can just do the algebra. It's up to you. And then number 7. Why do you think we learn something? So you can forget it? That's what it seems like in this class. What's going to happen in calculus next year? Okay, given the polar point, okay, why don't we draw the graph here? Hopefully you don't have to draw the graph after a 30-degree angle, and then you go 10 units from the origin. Then you measure off a negative 30-degree angle, and you go 6 units from the origin. So this is Q. And of course that's the origin, duh, 0, 0. Componentize vector OP and OQ, and then add them up and find the length. Okay, but in order to do this, we got to convert these polar coordinates into rectangular. You guys remember how to do that? X equal r cosine theta. I think we did this yesterday, yeah? Y equal. This is just the beginning of polar in this chapter, people. Hopefully you don't forget polar. Can we do this in our head? What's the cosine of 30 degrees? Times 10. 5 root 3. What's the sine of 30 degrees? Times 10. Okay, what about cosine of negative 30 degrees? Root 3 over 2 times 6. What's sine of negative 30 degrees? Negative half times 6. Okay, there you go. Convert it to rectangular coordinates. And then do what it says now. Componentize vector OP and OQ. Okay, how do you componentize vectors? Head minus tail. So what's head minus tail? Oh, head minus tail. 5 root 3. What's head minus tail? Oh, Mr. Park, when the tail is at the origin, it's easy. Duh. Okay, head minus tail. Head minus tail. Okay, now do what it says to do. It says add them together. How do you add these two vectors together? You add the x component. 8 root 3. Add the y component. You guys in physics, this is like you do this every single day. And now find the length of it. The bars around it, find the length. How do you find the length of a two-dimensional vector? The square root of this squared plus this squared. So what is that? 64 times 3, 192. Plus 2 squared is 4. That's the square root of 196. And we all know that's 14. Oh boy. And for those of you in physics now, and you guys are struggling with this, you guys better get your money back or something. Just make sure you have a receipt. Come on, don't you guys componentize all the time? What do you do then?
I don't know. I sit there.
Componentize! You guys don't make free body diagrams, Nakasone? You never made one free body diagram? Does this look familiar? Oh, I got a free body diagram. mg sine theta.
We never did.
Yeah, whatever. That's componentizing. Okay, I'm going to take this video and take it down to Mr. Kohara. So you guys know. Okay, so what you're supposed to, after last night's homework, you guys are supposed to be experts at two-dimensional vectors. Because now we're going to 3 dimensions and beyond. What other way? No, not yet. We got to get used to 3 dimensions first. So vector 3, okay, tonight's homework is all like the same thing except 3 dimensions instead of 2 dimensions. Now the other classes all told me that you guys learned 3 dimensions, right? X, Y, Z axis. Okay, that's good enough. Okay, in the Cartesian plane, that's the X, Y axis, right? So if I get a third axis that's perpendicular to these two, we call this the Z axis. So in 2 dimensions, the x and y axes divide the plane into how many regions? 4, and we call each region a quadrant. Come on, that's from algebra 1! First, second, third, and fourth quadrant, right? But now I get a axis perpendicular to these two. We call this the z-axis. So the x, y, and z-axis divide space into how many regions? 8 regions. Each region is called an octant. Here's the first octant, second, third, fourth. Then on the other side of the chalkboard, you got 5, 6, 7, 8. So which octant is all x, y, and z all positive? The first octant right here. X, Y, Z all positive, right? Where would x, y, and z be all negative?
4, 5, 6.
7. It's 7. Just keep counting till you get there. Look, 1, 2, 3, 4. Gotta be on the other side of the board, right? Because the z coordinates are all positive on this side of the board. On the other side of the board, in that room right there, that's where the z coordinates are negative, right? So octant 7. Now we're going to learn how to plot points. Okay, now when you plot point, you have the concept, right? Like, how do you plot the point 4, 3, 2? You go 4 on the x, 3 on the y, and then 2 on the z. So it'll be right at the tip of that chalk right there. Yeah? But then how do you show that on a piece of paper? We can tape up a straw and use toothpicks and stuff. No! You've got to be able to draw this on 2-dimensional paper. Now the standard way of doing it in mathematics is like this. Woo! Did we talk about this yesterday?
No.
Oh, we did it in the other 2 classes. There, right there. X, Y, Z. Now these are the positive X, Y, and Z axes now. Now can you understand what you're looking at here? Okay, suppose your eyeball is right where this chalk is. No, yeah, you see the tip of the chalk. This is your eyeball. And then you look toward the origin. You know what you see? That. You're looking into the corner of a room. Now, a lot of people going, Mr. Park, shouldn't it be like X, Y, and then Z comes out like this? Yeah. Yes. However, that's not the standard way in mathematics. This is the standard way. You got the XY plane here, and then the Z-axis is going up. I mean, this is correct as well, but that's not standard. You know what I'm talking about? It's correct, but it's not standard. We like to see the Z-axis going up. Okay, so how do you plot the point 4, 3, 2? So go 4 on the X, 3 on the Y, and 2 on the Z, right about there. Yeah, but then it can be anywhere though, see, right? Doesn't it? You can't even tell where it is. So that's why we draw the box. The key is you draw the box. So you go 4, 3, 2. And then you make a box. Mr. Masunaga taught you. The dimensions of the box are 4 by 3 by 2. And then you shove the box into the corner of the room. The coordinates at that point right there are going to be 4, 3, 2. In fact, the key to working with 3 dimensions is drawing the box, as you're going to find out. Because we're going to have other coordinate systems, just like in the rectangular coordinate system, remember we had polar? Now in 3 dimensions, it's going to have the same thing, except got 2, not just 1. And it includes polar. Everybody understand this? So you can plot points. Now, when I ask you to draw pictures, I'm only going to ask you to draw it in the first octet. Because when you got to plot negative, then it's really confusing. You know why? Because look, you have X, Y, Z. Like if you have to plot a negative X, then you got to go backwards there, which means you got to make negative, you got to go dotted line. Negative Y goes this way, the negative Z goes that way. And then it gets too confusing. So I'm just going to make you graph in the first octet only. You guys get it? So here's the point 4, 3, 2. How would you draw this vector though? This is a vector. You see the difference between the two? Every year students get confused. This is a point, this is a vector. How do you draw a vector with x component 4, y component 3, and z component 2? And just to let you know, this is the same thing as 4i hat plus 3j hat plus 2k hat. That just simply means the x component is 4, the y component is 3, and the z component is 2. But that's just the way engineers do it, okay? So how do you draw that vector? Here, you make a vector that goes from the origin to this point, like that. It's like the diagonal of the box. Get it? Because what's the coordinates of the origin? Isn't it 0, 0, 0? So how do you componentize a vector? You go head minus tail, head minus tail, head minus tail. There you go. That's the vector 4, 3, 2. Whew! Now again, the reason why we study 2 dimensions first is because it's easier, and then when we make the transition to 3 dimensions, and everything is similar. For example, what is this formula? This is the midpoint formula, right? So what do you think it is in 3 dimensions? And then 4 dimensions? And so forth and so forth, right? So you can do 2, you can go 3, you can go 3, you can go 4, dot, dot, dot. What is this formula? What is this? That's the distance formula between 2 points. So what do you think this is then? That's the distance formula between 2 points in space. So what is this then? This is the distance between 2 points in hyperspace. What's that? And I keep telling you, the 4th dimension is, okay, here's 3 dimensions. Make an axis perpendicular to the first 2. Okay, now, make an axis perpendicular to all 3 of these. That would be hyperspace. But you can't think of it in 3 dimensions because it's a 4-dimensional thing. Okay, I think we just better concentrate on 3 dimensions because otherwise your brain might explode. Are we getting the hang of it? What's this? What's this formula? Oh. That's the distance between a point and a line. So, what do you think this is then? That's a distance between a point and a plane in 3 dimensions. So, what is this then? This would be the distance between a point and a hyperplane in 4 dimensions. What's going on? What? Fall asleep? Is that what you want to do? Go sleep. Wake up later, watch the video. You guys weren't this tired first semester. What's going on? You're acting like period 3. That's what's happening. Okay, now what about vectors? Okay, yesterday we did 2-dimensional vectors. Okay, so let's say you have vector A. Now let's make 3-dimensional vector. 2, 3, 5, and then vector B is make up something. -1, -2, -3. Okay, I'm just making up stuff. Whatever you did in 2 dimensions, it's the same thing in 3 dimensions. Okay, how do I multiply a vector by a constant? If this is vector A, what is 2 times vector A? 4, 6, 10. You just multiply each component by the number. How do you add 2 vectors? Now they're 3-dimensional. Doesn't matter. What? Add the x components, add the y components, add the z components. How do you find the dot product? Same thing. You multiply the x components. You cannot multiply the x components. -2. Multiply the y components. Multiply the z components. And then add them up. -23. That's the dot product. How do you find the length of a 3-dimensional vector? So how do you find the length of this? Here's vector b. How do you find the length of it? What do you think? Well, in 2 dimensions, it's the square root of that squared plus that squared. So what do you think in 3 dimensions? It's the square root of that squared plus that squared plus that squared. 1 plus 4 plus 9, which is root 14. That's why we study 2 dimensions first. So when you make the transitions, all the formulas are very similar. You guys get it? Okay, now how do you, okay, so now we got vectors in space. I need another pen. We have 3-dimensional vectors. What did somebody tell me this morning? Who came to see me this morning? They said vector was a character in something. Like an animated movie, you know, computer-generated images. Vector. What's that?
Yeah.
Despicable Me, yeah. Who told me that?
Was it Hector?
It was Hector?
Vector.
Then who was the guy who came in this morning? Okay, whatever. Okay, now here's vector A and here's vector B. Now in space it's kind of hard to, but remember you can always put the vectors tail to tail, yeah, like this. Okay, find the angle between these two vectors right here. If I grab these two vectors and put them tail to tail, woo! Find that angle right there. Use the dot product again. The cosine of the angle between two vectors is equal to the dot product of the two vectors over the length of the first one and the length of the second one. So, how do you find the dot product of these two vectors? Well, we did it already. Came out to negative 23. Then you divide that by the length of vector A, which is the square root of this squared plus this squared plus this squared. So what's 4 plus 9 plus 25? Root 38. And then how do you find the length of this vector? It's the square root of that squared plus that squared plus that squared. But we already did that already. Root 14. So therefore, the angle is cosine inverse that. And you can do this in any dimension. If it's 4th dimension, you just tack on the 4th dimension. And so forth and so on. It's easy. So your homework tonight is to get used to 3 dimensions. Okay, so let's get used to. How much time have we got? 12 minutes. Okay, let's do some simple graphing. 2x plus 3y plus 4z equal 12. What is this graph going to be? I already told you. It's a plane. When you solve 3 equations in 3 variables last chapter, what are we finding? Where the 3 planes intersect? This is a plane. Woo! Woo, 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 woo. Okay, now, when you graph in 3 dimensions, okay, just like in 2 dimensions, what's the first thing you look for? What's the first thing you plot when you draw graphs? The intercepts. You plot the x and the y intercepts. So now we're going to plot the x, y, and z intercepts. Now, in 3 dimensions, how do you think we find the x intercept? Well, what do you do in 2 dimensions? How do you find the x intercept? You set y equal to 0 and solve for x, right? So in 3 dimensions, what do you think you're going to do? You set y and z equal to 0. How come? Because any point on the x-axis, isn't the y and the z coordinate equal to 0? Think about it. Just go a bit. Okay, so if I set y and z equal to 0, look, what is the x-intercept? 6. So here is the point 6, 0, 0. That's the x-intercept. What's the y-intercept? You set x and z equal to 0, 4. So here is the point 0, 4, 0. That's the y-intercept. And how do you find the z-intercept? You set x and y equal to 0 and you get, so it's 0, 0, 3. Okay, so this is a plane. That's the x, y, and z intercept right there. Okay, but there's more complicated graphs than just planes now. So it's not enough to just look at the intercepts. We also look at what we call the traces. Now what the heck is a trace? Now there are 3 traces. You got the xy trace, you got the xz trace, and then you got the yz trace. Now what the heck is that? The xy trace is where the graph intersects the xy plane. Think of this as a room. The xy plane is the floor right there. Okay? Where does this plane intersect the floor? How do I find that? What do you think I'm going to do? You said z equal to 0 because in the xy plane, isn't the z coordinate always 0? Any point in the xy plane, the z, because you don't go any up or down, the z coordinate is 0. So all you do is you set z equal to 0, and you get what? What is the xy trace? Set z equal to 0. 2x plus 3y equals 12. Hey, that's a line. That's right. So when the plane intersects the xy plane, it's just going to be a line like that. Of course, it extends forever, but this is just in the first octave. And likewise, what do you think the xz trace is? Here's the xz plane. It's like this left wall over here. Where does this plane, or whatever graph you have, intersect this wall? What do you think I'm going to do? You set y equal to 0 because every point on this wall, the y coordinate is 0. So what do you get? 2x plus 4y equals z. 12. Hey, that's a line. What? And then finally, the yz trace. Where does this graph intersect this wall right here, the yz plane? What do you think I'm going to do? Set x equal to 0, and then you get 3y plus 4z equal 12. Hey, that's a line. So you connect it with a line. And then now you use your artistic abilities. You shade. And there you go. That's the plane cutting into the first octet like that. You guys don't seem impressed. Okay, now, since we only got okay, I wanted to do more complicated graphs, but anytime you graph any three-dimensional graph, this is what you do. You plot the intercepts, and then you plot the traces. And then you can kind of imagine what the graph looks like. Okay, take out your, what is this thing called? iPad. Go to Pocket Cast. We are going to graph three-dimensional graphs now. Okay, new entry, 3D plot. Okay, type in this. Okay, now when you graph, I think you have to solve for z, you know. So you have to type in, I'm not sure. Somebody can experiment by just typing this in, but I think you might have to solve for z. So z equals 12 minus 2x minus 3y divided by 4. And I think you have to put the times in between here. 2 times x, 3 times y. I think you have to do that. I don't know. Why don't you experiment? And then press go, and things should graph a plane.
How do you work this? How do you? Where's Z?
Where's z? Good one. It's not April 1st yet. What the heck? It's good. Where's z? Are you joking me?
At the bottom.
There, ABC.
This the part. This looks weird.
3D.
Should be a plane. The plane, boss. The plane.
It looks kind of. Oh, there you go.
Okay, Lum got it on the screen. And then put your finger on it. You can grab it and you can rotate it and you can look at it from different views.
Whoa.
Put your finger, grab it and try to rotate it around and you can see different views. Like you can see the plane going like that.
Oh, I thought that was a north. What's your part? Look at it the wrong way. He looks like a north.
Oh, no, you have
The Z looks like a what?
Looks like a. Oh, you did that.
what Z?
Oh, come on. I walked all the way over there for that.
It looks like north.
So can you do like more than?
Yeah, okay, wait. Did everybody try to just punch it in like this? Did it work? Okay, you gotta solve for Z then. Just like on your calculator, you gotta solve for Y, right, when you graph. So in 3 dimensions, you gotta solve for it. Okay, let's do, a plane is so mundane. Okay, let's do something more interesting. Try to graph this. Z equals x squared minus y squared. I guess you gotta put raised to the second power, y to the second. Try to graph that. This is called a hyperbolic paraboloid.
You squared. Looks like a plus y
Minus. Well, if you do plus, you're gonna get just a paraboloid.
Oh, that's so cool.
This looks
Oh.
And then you can grab it, rotate it around, look at it from different angles.
Is this how they created the saddle?
Whoa.
Okay, keep that thought. Keep that thought. It looks like a saddle.
How they created the saddle.
Now you know why. Does everybody have the graph on the screen? Anyway, this over here, see? This is the hyperparaboloid right here. You see this point right here? They call that a saddle point. You know why? Because it looks like a saddle. But you know what's interesting about that? Okay, now you, in two dimensions, easy, right? Like, okay, you have a graph like this. What is this? What is this called? A local maximum, because compared to points nearby, it's the highest point. What about this point here? It's a local minimum. Okay, now think the 3 dimensions. Look at this saddle point right here. Is that a maximum or a minimum?
Minimum. Middle.
No, think about it. That point right there, compared to points nearby, is that the highest point on the graph or the lowest point on the graph? Well, it depends which way you look at it, right? If you look at it this way, that's the lowest point. But then if you look at it this way, it's the highest point. So that's why it's a lot of books, instead of calling it a saddle point, they call it a minimax. Because it's both a minimum and a maximum. That's crazy. Isn't it kind of neat? Okay, what time? How much time we got?
5 minutes.
Oh, and can you just touch it and it'll give you the coordinates of the point?
It's kind of hard to touch.
No, can't. No, I guess it doesn't. I guess it only does that on 2-dimensional graphs.
It's kind of hard.
You just gotta play with it. Okay, let's try. I know what I was gonna tell you. You know, in 2 dimensions, anytime you have a second degree equation, this one, ax squared plus bxy. We just studied this, yeah. X plus dx plus dy plus f equals 0. What is this graph gonna be? We just studied it, people. Conic section. Okay, but in 3 dimensions, okay, I don't want to write, okay, I will. Ax squared, plus by squared plus cz squared plus axy, we need a default, plus exz plus fyz plus gx plus hy plus iz plus j equals 0. Did I miss any terms? They're all second degree. Okay, so in 3 dimensions, what is the graph of a second degree equation? This is called a conic section in 2 dimensions. In 3 dimensions, these are called quadric surfaces. No, you guys are lucky. I don't think I'm going to do this. You know, 20 years ago, they had to identify the quadric surfaces. Like if I give you an equation, just by thinking about the intercepts and the traces, you got to tell what it is. Like, is it a hyperbolic paraboloid? Is it a hyperboloid of 1 sheet or 2 sheets? What does that mean, Mr. Park? Like here, because we only got 2 minutes left. Okay, you have a hyperbola. You guys know what a hyperbola is, right? What if I were to revolve it about this line right there? Revolve it. What do you get? Don't you get these, like, 2 cups?
Yeah.
We call that a hyperboloid of 2 sheets, because you got to make it out of 2 sheets. But if you take that same hyperbola and revolve it about this line, aren't you going to get this? That's called a hyperboloid of 1 sheet, because it's made out of just 1 sheet. Here, just graph this for 5 minutes. Quick. See, okay, just change that to a plus, just to see. Change that to a plus. Yeah, you should get a paraboloid. It should be like this. Parabolic dish. Can't you guys just edit it? Yeah, paraboloid. It's a thing. And then you can experiment by changing variables. You could put, okay, here, we got 1 minute. Throw some trig functions in. How about z equals sine x plus cosine y? Just for funsies. See what that, I don't know what this is. I would think it's going to have these, it's going to be like moguls. It's going to have these, it's like a, Yeah, you know, you guys know how to change the x min, x max, the y min, y max.
No. Whoa.
Yeah, oh yeah.
It's like looking at.
Can you pull it with your fingers?
Oh, that's so cool.
So yeah, so this thing just graphs three-dimensional stuff. It's like neat. That's why you get it for free. Otherwise, you gotta. The only way you can look at three-dimensional graphs, you gotta buy a TI-92. No, not 92. Yeah, TI-92, which costs what? $200. You get this for free. Plus, this does it way faster too. Okay, the bell's gonna ring already. So tonight's homework: get used to 3 dimensions, and then we're gonna start learning stuff. No, yeah, we are, but learning like high-level things.